Okay, thank you for giving up a little bit of your weekend to watch a math audio. This is going to introduce our topic for Monday. It is section 2.4, and it's called Real Zeros of Polynomial Functions. Basically, we're going to be solving complex polynomial functions and finding the solutions, otherwise known as the zeros. What I plan to do in this video or audio is look at the first two topics. We're going to review long division and the division algorithm, and we're also going to look at the remainder and factor theorems. I suspect that in Algebra 2 you had the division algorithm for polynomials, and you may have even had synthetic division. We're going to do synthetic division in class on Monday. I think the remainder and factor theorems may be new. I'm going to cover those today, and then we're actually going to cover a more complex theorem, the rational zeros theorem, that I think you'll find interesting in class on Monday. Why are we doing this? It is because finding the zeros helps us identify solutions to functions that can be, higher degrees than just the quadratics that you're used to solving in Algebra 2. First, editorial. I usually don't like to get involved in politics, but I do have a candidate I want you to consider for this November, especially if you're 18 and you can vote. Enough said. I am a Pinky and the Brain fan. So let's go back to division, and I'm actually going to take you back to 4th grade math, or 5th grade, depending what grade you're in when you learned it. First of all, when you had a division problem and you were doing long division, and let's just say you had 25 divided by 4, you would take 4 into 25, it goes 6 times, 6 times 4 is 24. Subtract the 24 and you have a remainder of 1. A few terms to review. The 25 is called the dividend. I will be using that word to describe the number that is being divided. The 4 is called the divisor. The 6 is called the quotient. And of course, the remainder is the remainder. And I'll get to a few other points with that. The book actually had a good example for starting us off. And if you recall, when we had a more complex long division problem, 3,587 divided by 32, I want to take you through this, the divide, multiply, subtract, bring down method of long division. If you're Laura and you've been to you're coming from another country, you've been taught a different division method, so she'll have to hang with me on this. But we basically take 32 into 35 one time. 1 times 32 is 32. We subtract, get 3, we bring down the 8. 32 goes into 38 again once. 1 times 32 is 32. This time we have a remainder of 6. Bring down the 7. 32 goes into 67 twice, and the remainder is 3. I actually want to express the remainder as a fraction, and the remainder is actually the answer is 112 and 3/32, because this remainder is what part of 32 is left over. Now I'm going to do the same problem or a similar problem, except I'm going to introduce variables, and we're going to have a polynomial function. Namely, I'm going to have 3x cubed plus 5x squared plus 8x plus 7. So there's our polynomial in standard form, and we're going to divide it by 3x plus 2. And maybe you see the parallel and the coefficients I used for this problem with the numbers that we were dividing over there. When we're doing polynomial division, we are focusing on the leading term, which is 3x, and asking ourselves, how many times does 3x go into the leading term of the dividend? So it's the leading term of the divisor. How many times does it go into the leading term of the dividend? As we subtract, we take it into new dividends every time. But 3x will go into 3x cubed, x squared times. The way I get that is 3 goes into 3 once, but we don't have to write the 1. X goes into x cubed, x squared times. X squared times x is x cubed. Some books will write the x squared over here and line up the x squareds. I personally prefer to line it up over the term we just divided into. To me, it keeps it straighter. you're welcome to use either method. I don't care where you place the x squared in the quotient. We then multiply. X squared times 3x, of course, is 3x cubed. X squared times 2 is 2x squared. We now subtract. 3x cubed minus 3x cubed, terms go away. 5x squared minus 2x squared is 3x squared. Repeat the entire, or bring down the 8x, and we repeat the entire process. How many times does 3x go into 3x squared? X squared divided by x is x. 3 divided by 3 is 1, so it's just plus 1x. Multiply again. And subtract. Bring down the 7. 3x goes into 6x 2 times. 2 times 3x is 6x. 2 times 2 is 4. Subtract, and we get our remainder of 3. But this time we write it as 3 over 3x plus 2. And we get rid of the remainder symbol and just write it as plus. In other words, just as when we divided before, we got our answer, our quotient was 112 and 3/32. Here our answer is x squared plus x plus 2 plus 3 divided by 3x plus 2. That was what was left over. And so that's how we do long division with polynomials. Let's go on, and if we have time to work a problem, we will. Well, why don't we do it right now with this problem? It's a little bit more complex, but it's worth doing. We have 2x to the 4th plus x cubed. I'm going to write the minus 3 out here, and I'll show you why. Second. And that's being divided by x squared plus x plus 1. Again, just as your divisor can be 3-digit when you're doing long division, our divisor with polynomials can be 3 terms, 4 terms, 5 terms, as many as you want, just as our dividend can be as many terms. Now, you may have noticed I left space in here. That's because there is no x squared term, and there is no x term. But I'm going to put a 0x squared and a 0x into the dividend so that as placeholders, so that when I divide, I don't forget those terms. I'm going to work this problem a little bit more quickly at first so that we can get through it and get on to the remainder and factor theorems. But if you want to pause this video and try it on your own, you're more than welcome to do so. X squared goes into x to the 4th, x squared times, and there's a 2. 2 divided by 1 is 2. I multiply, and I get 2x to the 4th plus 2x cubed plus 2x squared. I subtract. Goes away. I get minus x cubed minus 2x squared. Bring down the 0x. Next time. X squared goes into x cubed minus x times because of the minus 1. We get minus x cubed minus x squared minus x. At this point, I want to stop and show you a trick. Since we are subtracting, it sometimes gets confusing subtracting negative numbers. Remember, when you subtract a negative, that's the same as adding a positive. I am going to change all of the signs of these to positive and add them. Remember, subtracting a negative is the same as adding a positive. So if I reverse the signs, I simply add. And sometimes it cuts down on mistakes you might make with polynomial division. This becomes minus x squared plus x. Bring down the minus 3. Final step, x squared goes into x squared minus 1 times. So we get minus x squared, we get minus x, and we get minus 1. Subtract. Again, I'm going to use the reversing the signs trick and add, and everything, what we end up with when we add is remainder of 2x minus 2. So that's our remainder, 2x minus 2, which we can write as a fraction, 2x minus 2 over x squared plus x. plus 1. As I said before, I hope this is a review of what you had in Algebra 2. We'll work a problem in class as we get into synthetic division on Monday. Now, there is a theorem that is useful as a shortcut for finding out what the remainder is going to be for a given problem. And all we need to do is, if we are dividing by x minus k, where k is any constant. For example, you could be dividing by x minus 2. That's our divisor. I am going to take the number k, which is the opposite sign, since it's minus 2. In this case, k equals 2. And I'm going to plug it into my polynomial and see what I get. In other words, I'm going to do f of 2. In the previous example where we had the polynomial, let's do a simpler one. 3x cubed plus 5x squared plus 8x plus 7. Let's see, that one was 3x cubed, sorry. Plus 5x squared plus 8x plus 7. To evaluate f of 2, I simply plug a 2 in, which means I'm going to cube it. I'm going to square it. I'm going to multiply it times 8, and I'm going to add 7. This is 8 times 3, which is 24, 4 times 5, which is 20, plus 16, plus 7, and I get 67. If I were actually dividing that equation by x minus 2, I would have a remainder of 67. What this says is, if you want to find the remainder and you're dividing by x minus k, simply evaluate your function at k. Switch the sign from minus k to whatever the k value, from this minus k to k, and evaluate, and you'll have the answer. Let's try one to verify that it works. Find the remainder when 2x squared minus x plus 12 is divided by x plus 3. And in a minute, we'll actually do the long division, which is good practice for us. But in the meantime, I'm going to evaluate f of not plus 3, but minus 3, because remember the format is x minus k, and since my minus k was a plus 3, that means k is minus 3. And I can figure out what the remainder is by plugging in a minus 3. I get 2 times minus 3 squared minus a minus 3 plus 12. This is 18 plus 3 plus 12, and that gives me the answer of 33. I'm going to verify that now by doing long division. I'm going to do this fairly quickly. 2x squared plus 6x, subtract, I get minus 7x plus 12. This is going to be minus 7x minus 21. Reverse the signs and add, and we get 33. And as you can see, the remainder is indeed 33 over x plus 3. So the remainder theorem works. In class on Monday, I'd be happy to show you why it works and explain how the remainder of a division problem is the same as evaluating that problem at the divisor. But right now I want to move on to the factor theorem, which is even more important. It's like the remainder theorem, but it says, look, if you evaluate k and you get a 0, that means there is no remainder, and that says that x minus k is a factor of your polynomial. Let's try one so that you can verify it, and I think when you see that it works, it will make sense to you. So, for example, if I have the polynomial x squared minus 5x plus 6, and I divide it by x minus 2. I can first evaluate this by plugging in f of 2, and when I do that, I get 2 squared minus 5 times 2 plus 6, which is 4 minus 10 plus 6, and sure enough, That equals 0. When I do the long division, x goes into x squared, x times x squared minus 2x, subtract, and I get minus 3x plus 6, minus 3, minus 3x plus 6, and it works. There is no remainder. So those are our two theorems. The factor theorem that says whatever the remainder is can be found by evaluating f of k, and if f of k actually equals 0, it is a factor. So please bring any questions. Have these problems in your notes that you've done, taken them down, and you'll get credit for having done your homework over the weekend. And we'll go get into synthetic division on Monday and extend this. Thanks for taking your time to watch this.